Hey students, nice meeting you. I'm Alex, and as discussed today, I teach you about linear regression. And I also prepared a small Jupyter notebook, which you can check out on my GitHub repository. Yes, I want to go through four concepts. First, we learn only the parameter m and not the parameter b of our linear model. And our linear model has like this, usually this formula. So a parameter m times x plus b, where m is the steepness and b is the where it crosses the y-axis. Exactly, and first we only go by learning one parameter, so we assume our model goes through the 0 point, 0 on the y-axis, 0 on the x-axis, and we only learn the m parameter. Yeah, second we do both. We also learn the b parameter. On the third part will be, again, but with vectorization. So we give everything a little boost. And the fourth part is we compare the vectorized versus the non-vectorized version. And yeah, we will be more or less surprised. Feel free to interrupt me if you don't understand anything. And alright, let's get started. Linear regression from scratch. Okay, so we have a linear function. Usually I said this, but for simplicity we remove the bias term and we just learn this. So I started with generating some data, some random data, and here's a scatter plot, and here we have a linear relationship. Yeah. So, and now we want to make a model which minimizes the error, or we want to find a model that summarizes this data points with a linear model best. You want to find a linear model that fits best this data now. And so this is probably something with M3, but we just use this to generate the data. Now we are not using this value. So the goal is that our model figures this out by itself. So the m equals 3, so the steepness is 3. Yeah. Yeah, so we do not know that this is the case, so we say, okay, we think our m is -2, in this case I call it w, and we have a prediction. Our x points times the w, and this is our y hat, this is our prediction, and this is then looks like this. And again, it goes through 0, 0, as here, since we do not have any bias term. And yeah, both together, if we plot both together, it looks like this. Both go to 0, 0. Okay, so first we define the squared error. And yeah, as you see, this is like the actual input minus the prediction squared, and this for all the data points. That's basically it. And here we already have the algorithm, the training algorithm. In this case, it's gradient descent. So, all right. So what is going on here? So first we have a loop of the epochs. So we pass, first of all, the parameters. We pass the data, the ground truth, the weight. We start the twin. It's not necessary, but I already made it with -2, so I passed it for not confusing anybody, anyone. And the number of epochs. The epochs is how often do we look at each data point, and the learning rate. So epoch, yeah, we go through, say, 5 times or 100 times through every data point, and then we go through each data point. We say the actual data point, and we say the predicted data point according to our current weight. And here's the magic line. Here's where the magic happens. This is the gradient descent step, and this is the learning. The weight is updated with the weight minus some bit. This is the learning rate, and the gradient of the mean squared error. Since this is the measurement, our loss function, the measure of the differences in our case. Why do we use the squared error? We use the squared error since this has two properties, like small errors here are like getting less punished, or everything that is less than 1 is getting even less punished, squared. And bigger data points far away get more punished, so it's even worse if you're far away. And and the second property, the even more important property, is that these data points squared exactly is that we don't have any negative values, so our gradient update always goes in the correct direction. Alright, and exactly this is our derivative. So since the derivative is the change of our function at a specific point, and we want to go to the global minimum, and yeah, gradient descent does slowly do that. Alright, and if we do this, here, yeah, we started with having a weight of -2, if you remember both, and then it's getting less, and so does the more, and so the mean squared error gets less, and it's getting pretty close to 3. What was the steepness of the data we generated? You see here, okay, this, when we plot this exactly, and also I saved the mean squared error after every epoch. Okay, now the same thing with bias, with the bias. So as you see now here, there is a value at 2, so it's not 0, 0. So the at the x-axis 0, we're something different. We're not on the 0, 0 origin. So we have an initial guess, a random value I chose, since we do not know it in the beginning. We have our prediction, and we plot both. Okay, this does not look like it does model our data, and now it's exactly the same. The only thing that is different is this line here, since we also have a p-value, a second parameter, and here the derivative is different. We don't multiply it by x. I don't go into the derivative part, since you can just take the mean squared error and put it into the derivative calculator, and you will see that this is the formula here after the learning rate. You will get, yeah. Here again we can see, does it really nice. Okay, now doing the same thing but with vectorization. Alright, we again generate some data. We say, okay, 3 and bias is 2. This is correct. At 2 we are at 0. Alright, and we have an initial guess as before, doing this, and the mean squared error. And now instead of the for loop, we still go through every epoch, but instead of the for loop here going through each data point, we use the matrix multiplication. Here we have our weight, and we element-wise multiply it by x and add the bias term. This is our y hat. And here it looks quite similar, but it's different. We don't have any list functions here. Here we do the dot product and the sum, and this we can do since we have the numpy. This is numpy functions. This is the dot product as a shortcut. And here we can also do this since it's a NumPy function. Here there's a small test. The mean squared error of itself of some data points is always 0, 0, so this looks correct. And yeah, and we print it, and a nice loss curve. Here it looks. Now if we compare it, here I generated some more data. I made like 100,000 data points, and now I made the usual, the normal, the linear regression without vectorization. And here you see we need 3 minutes and 10 seconds, and if we do the same thing but vectorized, we take the same data set, but with the vectorized linear regression we have 2 seconds. Yeah, here we have 3 minutes 23 seconds, and here we have 1 second 35, 1.35 seconds. Yeah, so it's like a few hundred times faster. Yeah. Are there any questions? Maybe good to know, like linear regression is really very popular in statistics and really useful in machine learning. It's a very important part for neural networks, and every neuron basically does this. Every neuron in a feed-forward neural network has one part. This is a linear regression part. It has also every neuron also has a part which is a activation function, which is basically a non-linearity, since if it would only be a linear combination, functions which are functions of linear combinations, it would also result in a linear combination again. So you need some non-linearity so that you can also model nonlinear function, some wiggly functions. Yeah, I hope you have some insights into the topic. You can find the notebook on my GitHub repository. Thanks a lot, and have a nice day.